recording here. Okay, does anybody have any? I want to ask a question. So on the syllabus, I also have the take-home exam is supposed to be this weekend. When are your exams that you have for your other classes? When's the gauntlet? I know the students always have a gauntlet that next week, Wednesday and Friday. So everybody's got a lot of exams Wednesday and Friday. So if I bumped the take-home exam to next weekend, would that allow you to prepare for your other exams? Okay, then that is what I will do. All right, so then what's going to happen is the take-home exam will be next weekend, and then your final draft. So you're going to be working on it next weekend, and your final draft, while you're doing that, I'm going to be editing your rough drafts and sending you back my comments. Don't be intimidated if there's a lot of red. It's okay. The whole goal is to teach you how to technically write, so that way, all these job applications where it says technical writing skills, you'll have something where you can say, if you look at this link, you will see my technical writing skills. So it gives you another leg up in the job market. So I will bump this final, the take-home exam next weekend. Does anybody have any other questions before we go starting with lecture? I am going back to this screen capture recording instead of using Google Hangouts, because I know you guys look staring at my face for an hour and a half every Monday and Wednesday, and you get to do it again instead of actually seeing the course material. Thanks for bearing with me. I really have been trying to get the class moved over here, do the crazy setup with my. I hope that this is working out for everybody, and it's a positive learning environment. So on that note, let's go back to where we stopped last time. So we stopped. We were talking about subthreshold leakage, the different types of leakage in a circuit, right? So before, we had talked about what this body effect coefficient, surface potential, and threshold voltage, right? And so we had gone through this example question of 2.5 where we had this body coefficient, and we're trying to calculate if you put a certain amount of voltage on a body as opposed to ground, what's the new threshold voltage going to be? And so for review, what's the whole point of this threshold voltage? What occurs when you reach threshold voltage? It opens a channel, but even as you're applying voltage to the gate, you are beginning to push the charge carriers in the body down, right? So you are opening a channel, but what specifically happens at the threshold voltage in the channel? What's that?
A strong signal?
Well, it's a strong signal, but the strong signal permits what? Yeah, there's a specific term I'm looking for there. The flow of, if it's electrons, that means it's an NMOS transistor. If it's a PMOS transistor, it's holes. And that flow of electrons to the channel is called what? Starts with an I.
Inversion.
Inversion region, right? So if you have the body tied to ground, you have an initial threshold voltage that permits the creation of that inversion region. The body coefficient, surface potential, and the new threshold voltage equations are basically saying what happens when you change the threshold change the voltage on the body, and that becomes important because if you don't, sometimes there's all kinds of different ways of manipulating body voltage, positive and negative body bias. If you have negative body bias, you're reducing your threshold voltage, but you're increasing power consumption. If you have positive body bias, you're raising your threshold voltage, but if you use it at slower frequencies, it becomes more accurate. So there's pros and cons to manipulating this body voltage. But the other thing that you're learning at the introductory level, which is where we're at right now, is how that affects power consumption towards current that is not contributing to the logical execution of the circuit. So it's this body leakage. So there's three main sources. So did we cover 2.24 to start last time, or was Okay, we started 2.24. So we talked about subthreshold leakage, gate leakage, and junction leakage, right? So you all have this idea that you're relating it to the source and the difference between the source and the drain voltage. And so as you're increasing gate source voltage, you're dealing with this type of drain source current, and you have this dibble, right? Drain-induced barrier lowering here. And that means you have a lower barrier to overcome, which is not necessarily a good thing because you have to worry about, ultimately, there's the difference between 1 and 0. You need to have some sort of, we're going to be covering this later in lecture today, but there's a range that represents a logic 1, and there's a range that represents logic 0. In CMOS, and this is the reason why CMOS is still the dominant technology, it's much more clear when you get to a 0 and a 1, the rise and fall regions. In emerging technologies, particularly graphene, you'll have heard about graphene, has a lot of potential. The issue is the potential between logic 1 and logic 0 is much more difficult to determine. So as a result, you can get any type of error that you get in, any type of leakage, any type of wiring improper sizing of the transistors, and it becomes very easy to lose the logic. So that's why it's still an emerging technology, but proper implementation hasn't quite been determined yet. So we've talked about this junction leakage, where now we're relating this concept of the junctions acting as plates of a capacitor when you have diffusion in substrates. We talked about we're going to talk about band-to-band tunneling down here in TGO 2.25 in more detail. But basically, the whole idea is when we're inadvertently reverse biasing a junction. So, for example, when you have a body in an NMOS transistor, you are having it filled with holes, and you have electrons in your wells, right, in your drain and source. If you somehow reverse bias it because of this band-to-band tunneling, then you have some serious problems. And then gate-induced drain leakage and drain-induced barrier lowering. So you're putting some sort of strain on the drain for drain-induced barrier lowering. For gate, you have this drain leakage. That's a result of certain voltages being reverse biased. And so the amount of current conducted by a reverse diode, you have the source current. So you're using your Kirchhoff's law. You determine the current at the source of the transistor. And they have the voltage of the drain over the threshold voltage, e to that, and then you minus 1, right? Okay, so band-to-band tunneling. We formally define it as when it is occurring across a junction between the source or drain and the body when the junction is reverse biased. So it depends on the doping levels, which is why in section 1 we went into this in so much detail. And so you have this tunneling across heavily doped PN junctions. So we have this reversed issue, right? And so what's going to happen is if you've created an inversion region, right? And you have some sort of gate potential, and we have the silicon dioxide. And the whole idea is that you want to be able to create, in the case of an NMOS transistor, you're putting a logic 1 on a gate, and you're having a flow of electrons going through this inversion region from the source to the drain. Now what happens is the electrons are attracted by the potential on the gate, or can be. And so their natural inclination is to go towards the gate. But we don't want that to happen, which is why during the lithography process, we put that silicon dioxide in there, and we have a little bit of there. So we discussed in great detail about these gate capacitances, and we derived that equation that we have the cutoff, linear, and saturation regions. You have to be able to properly regulate them. Otherwise, what's going to happen is, as it's going through, they're going to start tunneling through. And as the transistor sizes get smaller and smaller, this becomes a much, much bigger issue, right? And so we have to worry about this a lot. In particular, here we're talking about gate-induced drain leakage. And here, when we have we have overlap of the gate and the drain. So basically what that means is in a conventional transistor, we have our source, we have our drain, we have our silicon dioxide in the gate, and we have our inversion region here, and everything flows through here. So what ends up happening is if you have this reverse biased and you start getting these regions growing and growing, or you don't account for them properly in your sizing, what ends up happening is these channels just end up merging instead of just creating an inversion region. And that's what's going on there. So therefore, here, this is why it says thwarts efforts to reduce subthreshold leakage using a negative gate voltage. The reason why that is because in order to, you want to be able to create a channel and then have a threshold voltage where that's created, and that represents where you start creating the flow, and that's where the logic changes from a 0 to a 1. So you have low logic, and then shoots up right around that threshold voltage. If that breaks, then you have this gate-induced drain leakage, and as a result, you have a ton of current that's flowing that does not contribute to the logical output because it's going through it's tunneling through the band. Okay, does anybody have any questions about that before I move on to temperature dependence? All right, so temperature dependence, you probably can think about it just intuitively. So at the beginning, we talked about the whole reason why we have current is because of these thermal vibrations of the charge carriers in the lattice structure, right? And so if you add more temperature, you get more thermal vibrations. It kind of just follows that way. So what ends up happening here is so we talk about conventional room temperature, and we have some sort of electron mobility that we've calculated before, right? So electron mobility relates to how fast and how mobile we're able to go through the silicon lattice structure. So we increase that temperature, well, guess what? We have the function of our initial temperature, and then we have our change temperature, and this Ku is a constant, which is approximately 1.5. So the electron mobility is going to become influenced by the temperature as a result of this. And so therefore, if you have higher electron mobility and the whole goal is to be able to create a scenario where you have a gate with a source and a drain, and this threshold voltage is where you're able to create the inversion region, right? Well, if you're increasing the mobility, then by definition, eventually they're going to want to get over here faster. So therefore, as the magnitude of threshold voltage decreases nearly linearly with temperature, and as a result, this threshold voltage of the temperature is our initial temperature minus this same constant of the initial temperature minus the new temperature. So kVt is approximately 1 minus 2 millivolts per Kelvin. So that's where, if you've got Kelvin here, and then you cancel the Kelvin out, and then you've got your volts, and that's how the equation is able to maintain its units. So that's the units will set you free right there. For those of you who didn't have me in 385, a thing I'll say over and over again, especially when you're solving these types of problems and you don't necessarily remember the equation, is the units will set you free. If you set up an equation, the first thing you should do is check your units. If you check your units and you go, all right, well, what's kVt? Okay, well, that's 1 minus 2 millivolts over Kelvin. And then, okay, so I want volts. This temperature here, that's in Kelvin. Well, I need to eliminate the Kelvin somehow. So that's where our constant comes through. So this little blurb is talking about the whole goal is how the current when the circuit is off is supposed to have high temperature, increases with temperature. So here's what that means. So a high VGS, that means we have, voltage. This is voltage source and this is voltage drain for an NMOS transistor, right? So at high VGS, let's say if we have this is tied to ground and this is tied to VDD. So that's this scenario. There's a negative temperature coefficient. That means it's going to decrease with temperature. So we already have a high current flow, right? But as this goes down, that means this VGS is going to decrease as well. And if you recall, the threshold voltage depends on our difference between our gate and our source. So when you have a 0 here and a 0 here, that means the transistor is supposed to be off, right? It means we can't create the inversion region. But as a result, you're still going to get these thermal vibrations. And that's going to actually influence flow through the transistor. So here it's saying as the current off, it increases with the temperature. So here, we're talking about IV characteristics of NMOS transistors at various temperatures. So as gate source increases, you can see the increasing temperature changes and there's an inflection point here, right? And so the current on decreases as here it's in Celsius. You'd convert it to Kelvin to make the equations work out. But the whole idea, and VNA is actually working on a really cool project with NASA on this. That when you get to certain temperatures, you're not able to get the proper amount of conduction with the output current. And the temperatures on Venus exceed the capacity for the CMOS that we're going to be learning in this course to be able to switch. So NASA is working on silicon carbide JFET transistors to be able to try to exceed these temperatures. They've demonstrated some of it, but they haven't done any synthesis algorithms, right? So you're going to learn a little bit about how do you actually synthesize a bigger circuit. Like you have your first synthesis algorithm that you learned in this course is how to develop the stick diagrams. And so there's a step-by-step, we're going to do this, you come up with, and so you've learned step one, you determine your pull up and pull down networks, and then you do your flow diagrams, and then you kind of connect those using your metal and P plus and minus diffusion regions, and then you develop your output. So that was actually a design automation synthesis algorithm that you did in that problem. So that's where that comes into play. If most of you probably aren't old enough to remember this, when they initially sent probes to Venus. This is like when I was a kid, and they didn't really account for this. And they wanted to get all these pictures of the surface of Venus, and it got there, and it worked for about 10 minutes. So we have precisely one picture of the surface of Venus from that first mission. They sent $1 billion, and it worked for 10 minutes. That did not go over terribly well. Okay, so this other thing we're going to learn about really quickly is geometry. So we're not just worrying about temperature. We now have to worry about the length and width of our transistor, because in order to create an inversion region, it has to get from the source to the drain, right? So if you make the transistor much wider, then the effective width is your drawn width, and then you're impacting it. So if you decrease it too much, well, that just makes it too easy. So you have to, that's why when you get down to 7 nanometers, making it work at that level can be kind of difficult. So right now, at the Intel Ivy Bridge is at 22 nanometers. So you recall that's our distance from our source to our drain, and this became 22, right? And so they were able to make that consistently work when you're accounting for these equations. So the orientation of the transistor. So here you start dealing with these concepts of FinFETs. I think that was a, yes, if I can, for those of you who are not familiar, FinFET technology is the double FinFET gate. So this is the layout of a multi-gate device. So that's what a FinFET looks like. And it's a little different than the gate, source, and the drain. Then you have 3D transistors. So you have all these different fin channels between the source and the drain. So you're worrying about, you have all kinds of different geometries that tie in. And these are ultimately multi-gate devices. So this is a double gate FinFET, FinFET MOSFET. See how these all have different geometries? And I think, George, is your group the one doing FinFET? I think one of your groups is doing FinFET, a FinFET presentation. Somebody's doing FinFET. I remember reading it in the proposals. A lot of people going like, well, I hope it wasn't me. Oh, 3D packaging. Okay, so so 3D packaging is kind of like we're looking at that other diagram. So FinFETs are pretty cool though. I think there's a grad video a little earlier. Is it? Okay, so that's quantum tunneling. It was earlier on in the course about FinFETs. So, this problem 2.6 here for linear mode, it's behoove you to thoroughly understand this question. And so it's a 6-part problem. But if you understand all 6 parts, you'll really understand the underlying. It shows you truly understand the underlying physics and how the equations work. So part 1, this is all in linear mode. If the width of a transistor increases, the current will increase, decrease, or not change. So if you recall this, we had derived this out where beta is the mobility and you have the permittivity of the silicon dioxide over the thickness of the silicon dioxide times the width, right? We went through this whole derivation. Also, I would recommend you should know how to derive this next weekend in theory. Hint, hint, wink, wink, nudge, nudge. But if you get down to this equation, you'll see that the width is directly proportional, right? So if we have our width of our transistor, right, as opposed to the length, which is going to be part 2, our current will increase. So for part 2, you just bring up that equation again. Will the current increase, decrease, or not change? Okay, well, if the length of the transistor increases, that means it goes up. So as L increases, the current from source to drain in linear mode will decrease. So for part 3, this one's a little more complicated. So we're talking about what happens if you increase the supply voltage of the chip. So the maximum transistor current will increase, decrease, or not change. So VDD increases. Remember, if you have your PLS transistor, so you have your source and your drain right here, right? And then it's going to be logic 1 on the output. So that means that your VD in these instances is going to increase. So this factor is going to make it increase more than this factor. Because if you multiply it, if you have think of it this way. If you have a number 10 minus 1, okay, so you're subtracting it by 1, but then you multiply that number by 10, does that increase or decrease? Or so multiply by 9, it increases by a factor of 9, right? Yeah, maybe you subtract by 1, but it's going to significantly increase it over here. So as VDD increases, so will the drain voltage, so therefore IDS increases. So the IDS, of course, is so in section 4, well, what happens to the gate capacitance? Well, gate capacitance is the oxide capacitance, which we determined. So we derive this voltage equation, then we determine the thickness of it, and then we have the width and the length. So this is unit. So as the width increases, so will the gate capacitance. Also, as the width of the transistor, as the length of the transistor increases, so will the gate capacitance. So just think of it this way: the more width you have, or the more length you have, that as a result, the more gate you have. The more gate you have, go back to the properties of capacitance where it's two plates separated. So if you have more plate, that it relates to the area of the plates as well as the distance between them. So if you create more area on the plate, that's where this ties into, this width and length here, this equation. So this last one is, if you look at this equation again, you have the oxide capacitance and the width and the length. Well, that does not have anything to do with the supply voltage, right? It's not part of the equation. So as a result, it was not going to change. So the ability of the of a material to hold a charge is not changed based on the supply voltage. So the analogy I would use is, if you think of a road has an ability to hold a certain number of cars, right? That doesn't change depending on whether or not you're in rush hour or you're at the middle of the night and there's only 1 or 2 cars, right? It's still going to have the same potential, same ability. And so if I were to have this take-home exam where I'm pretending to do a interview, and I would say, all right, the first thing I want you to do is I want you to derive me the equations for both PMOS and NMOS transistors for cutoff, linear, and saturation mode. Just show me the derivation, tell me why that works, and then I could give you a set of things like this where I say, all right, so now that you've done all the derivations and you've shown me all the different parts, go back through your derivation. If I say, all right, if I increase what happens to the drain source current if I increase the thickness of the oxide of the gate? What do you think happens? What's that?
You increase the thickness of it.
So I have the silicon dioxide between the gate and the body, right? I increase it. What happens to the drain source current? It's not part of 1 through 6, but you can solve it using the information you have. It decreases. Why?
Because then there has to be more of a supply charge to push the volt.
Right. That what you're saying is correct, but prove it mathematically.
So then,
yeah, look at what we have here. You can prove it mathematically given what you've already derived.
It's inversely proportional to VDS.
Yes, that is what George is pointing out here, Trey, is that in this equation, he is pointing to this thickness of this oxide here, right? As that goes down, what you said is true, and in an interview, I would say that, and what I'd say is, okay, so this is the physical. This is a really good point. if you want to, on an exam, I would highly recommend saying, okay, well, I physically understand it, and then I can also mathematically prove my intuitive understanding. So the yeah, so if your thickness increases, then this whole decrease. And so the whole goal in linear region is you want to be able to create this. So you have a certain amount of thickness here, but if you increase it, well, what's happening? You're creating more charge capacitance, right? You're also creating more of a distance between the potential voltage and keeping this down, right? So if you're creating more of an ability to hold a charge and you're pulling the distance away from the voltage on the gate, that makes it much harder to maintain this inversion region, right? As a result, we go back to our equation here. Thickness is going to impact our gate capacitance, which ultimately deals with the mobility and the ability to hold the charge. So the charge is going to be held there, which causes our current to decrease. So remember RC circuits, you're building up, you build up, you build up, and then you discharge. So what's actually happening as the voltage is building up, it's holding the charge and not permitting current. So here your current is actually increasing while this is decreasing, right? So your whole goal should be, as you work through that derivation, you should be able to go like, okay, well, this is a certain part, this ties in here, and you should be able to say, as a result, so if I have gate and source, right? So here, let me ask you another thing. We've done mobility, we've done gate. So for some reason, our gate voltage, there's some sort of leakage on the gate. As a result, that causes our voltage on the gate to decrease from the supply voltage to 80% of the supply voltage. What happens to our drain source current? Okay, so so it's an NMOS. Let's say this is an NMOS transistor, right? And in ideal situation, you want to have a gate equal VDD, right? But you have some sort of leakage, so therefore your gate voltage is decreased. So the amount of voltage applied to the gate has decreased from 100% of VDD to only 80% of VDD. Does the IDS current increase, decrease, or not change? Well, VDD is going down, but I'm saying that it's not VDD's, I'm saying the gate voltage has decreased.
As long as it is still greater than the threshold.
Right, well, that's not what I'm asking. All I'm asking is, will the current increase, decrease, or not change? Decrease is why, Josh? I think Josh has the idea here.
Because if the gate voltage decreases, it's going to multiply by the drain voltage as well. Mm-hmm. So
VGS, as a result, is going to go down, which is going to cause this quantity to go down, which is going to cause IDS to go down. So then what's physically happening here? Well, instead of having the complete voltage here, we're only applying 80%, which we're only applying, so we're repelling the body charge holders by 80%, right? Which means that's only 80% of our ability to create that inversion region. So as a result, the current is going to decrease. So do you all see what I'm saying about how you can kind of look at these equations and pick different parts? What happens when what happens when I have some sort of spike on the drain? What happens when I decrease the thickness? What happens when I increase the width of the transistor? What happens if I choose a different, this should be easy. What happens if I choose a different charge carrier with different mobility? What's going to happen to the current?
Could that exactly just cause a gate-induced drain leakage?
Yes. So what I just described is GIDL. That's one of those things that if you put that on exam, we'll go, ah, they really get it, plus extra. All right, so does this make sense now, kind of what we're tying in here? All right, good. So this idea of DC transient response. So what's going on here is digital circuits are merely analog circuit. Oh, wow, that was a lot bigger than I expected it. So analog, we worry about everything on all of the region, right? So we have this analog circuit. Whereas with DC, we have a logic 1 and a logic 0, and we are trying to, ideally, we would want it to go from, ideally we want it to go from here to here, right? 100% of the time, 100% of VDDs and hits ground. But that is not always going to be the case. What we're going to be learning about is we're going to be learning about these different regions up here, where if you reach up here, you can consider this a logic 1, and here you can consider a logic 0. So this is going to be 85 to 90% typically, and this is typically going to find this as 10%. And when we start getting into the labs, you're going to see how this really applies to how, because a lot of the technology files that govern how you're going to simulate your circuit have this information in there, and have it in there for specific cells. So you design a 2-input NAND gate, you design an inverter, you design a 2-input OR gate, design an adder. All of these have specific sizes. It has the width of the cell, the length of the cell, how big you want this to be, and based on that, you have to apply a certain amount of power in order to get this done, right? So all of that ties into this DC transient response. So here we've talked up to this point about inverters. Here we say that VDD is always 1 and VSS is always ground, right? What if they're not? And then we had these equations for IDS is 0 and the gate source voltage is less than the threshold voltage. Your gate source voltage exceeds the threshold voltage, and IDS increases with VDS. So we increase that, the difference between that drain and that source voltage, and that linear region increases. And then we have that saturation region, right? But what happens when we don't have an ideal situation? What do we have to do to make this transistor still work? And so these next topical guide objectives for NMOS and PMOS here describe precisely what this is going to be. So for our cutoff region, you have our gate source. This is GSN and N is NMOS, right? So GSP is for PMOS. So now we have to worry about what the actual VDD is as opposed to the input voltage. So if we have an input voltage, our input voltage on the inverter, we want it to go from a logic 0 to a logic 1, right? So if we had 0.18 micron as our feature size, and the supply voltage is 3.3 volts, we would want the input on the inverter to be 3.3 or 0, correct? So let's say we have a scenario where 3.3 and 0 is met, but for some reason the supply voltage exceeds 3.3. It becomes 3.6 for some weird reason. So here, for the linear region, threshold voltage is going to be equal to the V out is going to be less than the input voltage minus the threshold voltage. And the reason why that's because we have the gate source for the NMOS transistor is greater than the threshold voltage for the NMOS transistor. So as a result, the input voltage, which is gate, is going to be greater than the threshold voltage. And drain source of the NMOS is going to be less than gate source of the NMOS minus the threshold voltage. right? So we have this input of 1, threshold voltage of about 0.77, right? So that should be approximately 0.23. So that means we're going to want that difference between the drain and the source to be less than that for this to be a linear region. Otherwise, we'll reach saturation. And lastly, for the saturation region, you have your, again, our gate source difference is going to be greater than the threshold voltage. But as we reach this input threshold voltage in our drain source region, in the saturation region, the output voltage is going to be greater than the input voltage minus the threshold voltage. So again, we put a 1 on an NMOS transistor. We have a threshold voltage of like 0.23 or 0.77. If for some reason that difference is exceeded by V out, that means we have some phenomenon going on the drain of the NMOS transistor, which is causing us to go into saturation. Whether our fan out has too much load capacitance, whether we've tied an inverter onto a huge circuit and that's just causing a tremendous amount of pull on it. There's all kinds of things that we're going to be learning out in the next few sections that could potentially cause this. But here, deriving it, I made the derivation a little simpler for the PMOS transistor. Cutoff, the input voltage is going to be greater than VDD plus the threshold voltage. And if you recall, the threshold voltage is, the VDD is going to be 1, but that threshold voltage is going to be smaller. So linear, the input voltage is less than the sum of these because we had negative numbers. And when V out is greater than that, we are in linear region. But when V out becomes less than that, that means we've saturated the PMOS transistor. And so, as we recall, also remember since the mobility of holes we've assumed the mobility of electrons are twice that of the mobility of holes. So we doubled the width of the PMOS transistor to account for this. So here's this diagram I've been alluding to for the past few sections. So here we have the supply voltage, and let me pick a better color. So we have supply VDD, negative VDD, and the increase in drain source current and drain source PMOS, right? So this is the NMOS and the PMOS transistor. So in the NMOS region, what ends up happening is we have VGS for each of these, we have different values. So this could be 0.2, 0.4, 0.6, 0.8, and 1 volt. Or those numbers times the factor of whatever VDD is. And so as we increase VGS, our VDS increases, and these are our IV characteristics. And those are all dependent upon those regions. So then the same thing, gate source for PMOS, which is down here, by doubling the transistor length, we get essentially the same transistor characteristics, except they're inverted. And so when you put them like there, basically this chart is the last chart, except you are doing the absolute value. So then here what happens is as you get closer and closer to VDD for VGS, the PMOS transistor goes down in terms of this current. Anyways, when you think about it, you put a 1 on a PMOS transistor, get cut off. So there you go. There's the physical application of what we covered in section 1. Same thing, because it's an NMOS transistor, it inverts. So this table diagram here, we're going to be talking about transistor operating regions. And so we have some regions where we want this to work, right? So here, this is actually doing the NMOS transistor. So let me go back up here real quick. So if you look here, you see I kind of starts out and increasing and decreases. So here's what's actually going on when we have a output is the output is VDD to 0. So when we start in our inverters, this is an inverter. So each part of this table, we have a PMOS device and an NMOS device. And so each one of these, and you can derive this. So you're starting out, you put a 0 in on the input. So we're going to have our P, so it's below the threshold of the NMOS device. But it's definitely, we've definitely exceeded the threshold of the PMOS device. So the PMOS device is on and the NMOS device is off. So what's happened is our PMOS device is in linear and our NMOS device is in cutoff. So that we have created an inversion region in our PMOS channel. The NMOS transistor is in cutoff. And so the output voltage is going to be VDD because you're going to have the flow from the supply voltage to the output. So then we get into this. Ideally, we want to get from B to E very quickly. But we have to account for all of these in our design. So when we've exceeded the threshold voltage of the NMOS transistor, meaning the threshold voltage is less than Vin, which is less than VDD over 2. So we haven't reached VDD over 2 yet, which is where this one brief place where region C is. So here we are still in the linear region of the PMOS device, but we've saturated our NMOS transistor. So that's going to start bringing our output voltage down because we're no longer just cut off here, right? We have to worry about this transistor now. So it's actually, we're going to start getting a little bit of some pull down. And so you can see here in this region in section B, V out's still going to be greater than VDD over 2, which is where this ties in. But then we hit section 2. This is where VDD is, where Vn, the input to the transistor on the gates, is equal to half of the supply voltage. At that point, we have saturated both transistors. And the reason why we can say that is because remember the threshold voltage for both NMOS and PMOS is it's either 77% or 23% of the supply voltage for the NMOS and PMOS, respectively. We've gone below that because we're just at 50%. So we've saturated both transistors. We are halfway, and it's going to sharply decrease. So then we get to the same point where we've inverted everything. Section D is just the same as B except the other way. We have our input voltage is less than Vin over 2, which is of course which is less than VDD minus the absolute value of the threshold voltage of the PMOS transistor. So we're in this region where we now have the NMOS transistor. The NMOS transistor is now on, right? So we now have a flow of electrons here. So the current definition, as you recall from electronic circuits, is defined as the opposite directions, the flow of them. And we have this non-ideal region because section D has saturation in the PMOS transistor. And then we exceed the threshold voltage for the PMOS transistor. So that goes clearly into cutoff. And then the output is equal to VSS, which is typically going to be voltage of 0. So we want the overwhelming majority, okay, we want the overwhelming majority of our operation of an inverter in A and E, right? And being able to provide efficient switching and dealing with the IV characteristics is where we eliminate this as much as possible. You can't avoid it, but it's there. So efficient switching is important, and all of these gate capacitances and all of these junction capacitances and these body in the tunneling and body biasing and all of this different stuff contributes to why you're going to have leakage in regions B, C, and D. And so this is when, especially when we get into subsequent sections where we start dealing with transistor sizing. And for example, we talk about beta ratios here. We're going to worry a lot about that. And the more you worry about that, the more you spend your time in A&E and less time everywhere else. For example, right here, skewed gate. This is actually right what I was talking about here. When you don't have that these beta ratios, remember mu n over q is equal to 2, right? So that means we doubled the width of the PMOS transistor, and that allows our beta ratios to become the same. Well, what happens when you exceed, or when it's not on? So VDD here, so this is this one here is when it's 1, right? So you see how we have equal region operation for A and E when it's 1, right? So if your beta ratio is below 1, that means you're going to be spending more time. That means you have a circuit that's dominated by the NMOS transistor, right? So as a result, so it's dominated by the NMOS transistor. So here, when it's below 1, you see how it only stays in the PMOS transistor for a little while and spends the overwhelming majority of the voltage in the NMOS region. That's what happens when your sizing is not appropriate. Likewise, when you're dealing with the PMOS transistor, if you put PMOS too high, right here, you spend a lot of time in PMOS region and then only a little bit of time in the NMOS region. So by maintaining these ratios, you're able to optimize your switching. So the more time you spend between here and here, and the less accurate you're able to make these, that's more leakage, that's more power consumption that doesn't contribute to the overall function of the circuit, inaccurate switching, whole 9 yards. Okay, so I think I've got one other page after this, or we can do these 3 problems, and that should bring us to the end of the lecture. Okay, so for the first part, as an engineer has proposed the circuit that's shown to the left. He calls it a non-inverting buffering circuit, or he or she, which inputs the same as the output with a desired timing delay. Assume the beta of the PMOS transistor equals the beta of the NMOS transistor, and the threshold of the NMOS transistor is equal to the absolute value of the threshold of the PMOS transistor. What will actually happen when this circuit operates in each region of the operation? So I'm going to minimize this. See, people are furiously copying. I want you to think about it for a split second. Josh in particular, I'm calling Josh out. But okay, so we have our inverter, right? So we have a PMOS and a pull up and an NMOS and a pull down. So what has happened is this engineer is flipping these around. We're putting the NMOS in the pull up and the PMOS in the pull down. So I put a logic 0. So I put a logic 1 on the inputs. So what happens to the NMOS transistor? So the NMOS transistor now has a 1 on it, right, on the gate. But what's on the source?
1.
It's a 1. And what's the characteristic of the NMOS transistor? It's not just what you put on the gate, but it's what goes through the channel too, right? So what's actually happening?
Nothing.
Well, how do we? There you go. And what do we actually call this?
Depletion, everything.
So here, we'd want this. So I've written more than I would expect on an exam. But here I said what we would want if the engineer, actually you might want to include this anyway, because here's what the engineer is hoping would happen in the blue box. The engineer is hoping that the P-bias device is in linear, is in cutoff, and the NMOS device is in linear, saturated, and then you achieve the exact opposite, right? Because it just reflects the TGO. That's what they're hoping happens. However, here's what's actually going on. What you all just said. You use the equations, but since Vn is 0, it's not possible. Remember, cutoff for PMOS, we want Vn to be greater than the threshold voltage of your transistor, right? So, oh, that's way too big. So in this section up here, what we're saying is for when 0 is less than or equal to Vn is less than or equal to threshold voltage, we want cutoff for the P device in linear, so we have an output voltage of V. However, the cutoff for PMOS here must meet that the input voltage must be greater than threshold voltage. But since the Vn is 0, that's simply not possible. So therefore, you can't have cutoff in that region. Likewise, linear for NMOS, the gate source voltage must be greater than the threshold voltage. However, since Vn is greater than the threshold voltage plus VDD, since Vn is 0, that means that's 0, it must be greater than 1. Therefore, it's simply not possible. So already in that section, you can tell the engineer that their design sucks. But unfortunately, your crazy CMOS professor has asked you to describe what's happening in each region. So here's the rest of the regions, right? So you just go through those equations and you say, in algorithms, you call this proof by contradiction. So the first thing that I wrote, I say, here's what the engineer is hoping happens. They're hoping we get this cutoff region and linear region, so that way we have logic on the output. And in order to do that, we must meet these equations as described in the topical guide objective, right? So this is how we would define it. And it has to work because we're going from 0 to the threshold voltage in region A because we want it to match our input, right? So basically all we have done in this first section is take this topical guide objective and just flip it on its head. Right? So we basically see this is cutoff and that's linear, saturated, linear, saturated, saturated, linear, saturated, linear cutoff. That's what the engineer has proposed, right? Does everybody make sense of that? So I just took these same equations here and flipped these around because that's what they're hoping. And then as a result, in this drawing here, you can see that I have basically done that same thing where I have just inverted the diagram. So that's what the engineer is hoping would happen. And then in each section, you go and say, actually, no. Can't do that. Bad engineer. Here's why. Section A is not going to work because you need that input voltage to be greater than the threshold voltage in order to have cutoff for PMOS, right? But since your input voltage is 0, that's not going to happen. Same thing for linear, you need that gate source voltage to be greater than your threshold region, which means that the input has to be greater than your threshold voltage plus your VDD. But since your input voltage is 0, that's simply not possible. And you see there's a lot in the rest of this proof, not possible, not possible, not possible, not possible. The only thing that works is region C. That one spot right in the middle when VDD over 2 works because they're both saturated. That's the only time their design works properly.
So for it not to work, you just have to have two
two inverters in series.
Yeah, you would put, if you wanted to create a non-inverting buffering circuit, you could say that on exam. You could say, actually, what you want to do is you have your concept backwards, so you can invert it, but then you can invert it again and try to get that same timing delay. So yeah, just go back through and then you look at these equations, right, here, and you say, actually, now we need, so section D, we would need the P device to be linear, right? However, that's simply not going to work because we've violated these constraints. So to go through the rest of this, section D, for linear for PMOS, that means we would need the gate source for PMOS to be less than the threshold voltage of the PMOS transistor. That means the input voltage on the gate has to be less than the threshold voltage. However, since VDT over 2 is always going to be greater than the threshold voltage of a PMOS transistor, that's simply not possible. Same thing saturated for NMOS. It's not possible for this condition. The gate source voltage has to be greater than the threshold voltage with VDD. And likewise in section E, our gate source voltages are less than threshold voltages in both cases. And since it's inverted, it's just not going to work. So we have proven that this engineer's proposed design is not going to work for what they want. And so I would encourage you, as you guys are kind of working over and studying, go through both of these, compare it to the topical guide objective, and if it's not making intuitive sense, come find me, and I'll be happy to go over this again. All right, so again, I have these diagrams which are showing what's actually happening. So remember, this is the one we actually want. So that's the properly working inverter, and the engineer has tried doing this, and there's no region where it's actually working properly. So here we have these regions. These are your linear regions, right? So here's your linear region for your PMOS transistor, and here's your linear region for your NMOS transistor. And notice how the final simulation has no linear region. So we've proven mathematically it doesn't work. We've proven intuitively understanding the channel, how the channels work, by saying, okay, well, you're applying the voltages wrong, since we know that PMOS transistors are poor conductors of zeros. Then it wouldn't work anyway. So we know it physically. And we have a simulation here that proves it doesn't work as well. So we've proven it in literally every possible way. And, oh no, we can get noise margins covered in 7 minutes. So this whole idea that I've been talking about, we're trying to get from a pull-up region here. So we have to get to this 1 and 0, and we have these little regions here that count for, this is a logic 1 and this is a logic 0. These are defined as noise margins. Right? So noise margin is the allowable voltage range on the input of a gate where the output will not be corrupted. So this is defined as the regions where it'll still work. If we get it in there, we can account for it properly. And 2.29 is just the notations. IHL is the minimum high input voltage. So this is VIH. So VIL, the maximum low input voltage, VIL. VOH is this one, and VOL. So VOH and VOL ideally would be your supply voltage and ground. And so your noise margin for your lower region is just equal to VIL, which is this one, minus VOL, which is here. And then noise margin high is equal to VOH, which is this one here, minus VIL, VIH, which is this one here. So that's just a formulaic description of what this little chart that I've drawn over here describes. So Also, I made a little note here that this region in the middle is known as the indeterministic region of the forbidden zone. Forbidden zone sounds like something more out of Star Trek or something Deadpool might want. I don't know. All right, so that doesn't work in class. All right, so leave the Deadpool jokes to George. All right, so let me scroll down so you guys can see this. But here, okay, so this is basically just drawing out a formal drawing of what I just did here. And so what we have here in our is that we have our region A. We reach this point where we reach region B, right? So we have saturation in the circuit. So these high voltages and low voltages are determined to when we're going to hit the saturation region in the opposite pull-up or pull-down network. So if we're in the pull-up range, or high voltages, we start hitting saturation in the NMOS transistor. That's when we exceed our noise margin. So also, the other good thing about this diagram is you want your input and output regions to contribute to these, you want the output characteristics to be more accurate, right? So here we actually have a non-inverting buffer. So we want to make sure that whatever region we get into when we put the input in here, it has to reach an appropriate output noise margin. So I think the last question that I have here in the section, this is the end of section 2, is just a plug and chug type question about noise margins. So example 2.8 is a novel inverter has the transfer characteristics shown in figure 2.34, which is from the textbook and is this guy here on the left, right? And so the high region here is 1.2, and VOL gets down to 0.15. The high is 1.05, so that's going to be about here, right? And IL is 0.3. So 0.3, let me delete all these. So 0.3 is about here, and then 1.05 is about here. So we have our regions, right? So then just find our noise margins. So this just becomes 1.2 minus 1.05. So our noise margin is 1 volts. Likewise, 0.3 volts minus 0.15 volts is also 0.15. So in a properly designed circuit, we want these two noise margins to be the same. So, does anybody have any questions on what we've covered today? Like, no, dismiss us, please. All right, so I have recorded the screen.